Assalamu alaikum. Hello dear students, in our last part in chapter 7 vibrations and waves. By the end of this video, you will be able to classify waves according to their types and nature and to recognize the electromagnetic spectrum. Let's start by performing a quick revision. In the previous video, we have defined waves as perturbation that propagates in a medium, like water waves and a wave on a rock. Also, we have listed the characteristics of waves, such as the wavelength, which is the distance covered during one period t. Also, we have learned about the speed of propagation of the wave, which can be calculated by dividing the wavelength by the period of time, or multiplying the wavelength by the frequency of the wave. Note that the maximum displacement of a wave is called a crest, and the minimum displacement of a wave is called a trough, and the distance separating two consecutive crests or two consecutive troughs is the wavelength lambda. But actually, do all the waves propagate identically? And do they have the same nature? Let's start with our first objective about the types of waves by observing the following videos. In these two videos, you need to focus on the direction of the particles' vibration, and here we are talking about the particles of the rock, compared to the direction of the wave's propagation, where in both cases the wave will propagate forward. Let's observe together. Notice the direction of the particles' vibration in this case. Let's observe the second case. Also, the wave propagates forward, but the particles vibrate in a different way. In the first video, the wave is called a transverse wave, whereas in the second one, the wave is called a longitudinal wave. But what is the difference between them? To distinguish between a transverse and a longitudinal wave, let's start by observing the following animation. In this case, you need to stress your focusing on a red particle, on the movement of a red particle. We have two different directions. The direction of the particle's vibration is up and down, whereas the wave propagates forward. It's clear that in this case, particles of the medium vibrate in a direction perpendicular to the direction of propagation of the wave. This is a transverse wave. Whereas, if we have a closer look at a longitudinal wave or longitudinal wave, you can notice that as the wave propagates forward, the particles vibrate in a direction parallel to the direction of propagation of the wave, and this is a longitudinal wave. An example on a transverse wave is water wave, and an example on longitudinal waves are sound waves. Now let's have a small remark while talking about the types of waves. Actually, when we represent transverse waves, we will represent them as set of crests and troughs, where the distance separating two consecutive crests or two consecutive troughs is the wavelength lambda. Whereas when representing a longitudinal wave, we represent it as a set of rarefactions and compressions, where the wavelength is measured between two consecutive rarefactions or two consecutive compressions. Please take care for the following remark. When we represent a wave by a graph, we usually represent it in two different forms. In the first form, the graph shows us the variation of the elongation of the particles of the medium as a function of the distance traveled by the wave. Such graphs represent the elongations of all the particles of the medium at an instant t, and from this graph we can indicate the value of the amplitude and the wavelength of the wave. In the other form, the graph may show us the variation of the elongation of the particles as a function of the time in second. In this case, the graph represents the elongations of only one specific particle of the medium during the time t. And from this graph, you can indicate the value of the amplitude and the period of the wave. Note that the first graph represents a transversal wave, whereas the second graph may show a transversal or a longitudinal wave. Let's now distinguish between the different natures of waves. The first nature is mechanical waves, like water waves, sound waves, a wave on a rock. Such waves are vibrations that propagate in a material medium. They are not capable of traveling in vacuum. These waves need a vibratory source to be produced. They could be either longitudinal or transverse. Note here that since we have mentioned that the speed of the wave depends only on the medium where the wave propagates, then the speed of the wave varies from one medium into another. Here, since mechanical waves need to propagate through the particles of the medium, then the denser the medium, the faster such waves propagates or travel. The second nature of wave is electromagnetic waves, like light waves, like microwaves, radio waves, etc. These waves are produced by oscillating charges. They do not need a material medium to propagate. They are capable of traveling in vacuum with a constant speed, c equal 3 times 10 to the power 8 meter per second. Note that c is equal to lambda times f. In other mediums, the speed is smaller than c. Here, when we talk about electromagnetic waves, the denser the medium, the slower such waves travel or propagate. Also, you need to know that these waves are characterized by their frequencies, and they are only transverse. If you are asked to distinguish in a certain question between the different natures of waves, you can focus on two main ideas. The first one is that mechanical waves need a material medium to propagate, whereas electromagnetic waves are capable of traveling in vacuum. The other one is that mechanical waves can be either longitudinal or transverse, whereas all electromagnetic waves are only transverse waves. Let's move now to our second objective about the electromagnetic spectrum. The electromagnetic spectrum takes all the electromagnetic waves and lines them up based on their wavelengths or frequencies. This spectrum arranges the electromagnetic waves from the longest wavelength, which corresponds to the lowest frequency or lowest energy, to the shortest wavelength, which corresponds to the highest frequency or highest energy. You can see in increasing order of frequencies, radio waves, microwaves, infrared radiation, the visible spectrum, ultraviolet radiations, X-rays, gamma rays, and you have above them applications on each one of such waves. Note that the visible spectrum shows the visible radiations with frequency ranges between 3.75 times 10 to the power 14 Hz and 7.5 times 10 to the power 14 Hz. In vacuum, where the speed of light is c equal 3 times 10 to the power 8 meter per second, the range of visible wavelengths lies between 400 nanometer and 700 nanometer. But this range is only true in the case if the medium where the electromagnetic waves are propagating in is vacuum, whereas the range of visible frequencies is always true. Let's notice now the visible spectrum. You can see in this animation that the white light is the mix of all the visible electromagnetic waves. Upon passing through a glass prism, it is separated into its constituent colors. We say that the spectrum of white light is obtained through a prism. Let's practice now by solving the following application. But before I start, it's important for you to test yourself by pausing the video, reading the application carefully, and trying to solve it by yourself before you watch the solution of the application. Let's start with application 4. A point vibrator S performs 2,400 vibrations during 1 minute. This source creates waves on the surface of water, such that the distance between the third and the fifth crest along the same ray is 12 cm. In the first question, you are asked to specify, which means to indicate and justify, the nature and the type of the water wave formed on the surface of water. Since it is a water wave, then its nature is a mechanical wave, since it needs matter, which are the particles of the water, to propagate through or to travel through. And it is a transverse wave, since the particles will vibrate in a direction perpendicular to the direction of the wave's propagation. Now you are asked to calculate in the second part the period of the wave, then to deduce its frequency. To calculate the period, we will review the formula used to calculate the period, which is the period is equal to delta t divided by n. Here you have the number of oscillations or vibrations or cycles, which is 2400, and the duration of time, which is 1 minute. But we need first to convert the time into the SI unit. From minute into second, we multiply by 60. Then apply the formula. T is equal to delta T divided by N is equal to 60 seconds divided by 2400, which gives us 0.025 seconds. Since you are asked to deduce, then we need to use the value of the period you have calculated. Then we will use the formula F is equal to 1 over period, which gives us 40 Hertz. And don't forget to write the units. In the third part, you are asked to calculate the corresponding wavelength. Here we need to draw a small sketch for the given. They gave us that the distance separating the third and the thick crest is 12 centimeters. Drawing a sketch for the figure, you can count between the third and the thick crest 3 lambdas or 3 wavelengths, and this wavelengths corresponds to 12 centimeters. Then lambda is equal to 12 divided by 3, which gives us 4 centimeters. By converting it to the SI unit, we obtain 0.04 meter. In the last part, you are asked to deduce the value of the speed of the wave. You can calculate the speed by applying the formula, either by dividing lambda by the period or by multiplying lambda by the frequency, and all these factors we have calculated their values in the previous parts. Then V is equal to lambda times F is equal to 1.6 meter per second. Let's solve another application. Also pause the video and try to solve it by yourself. A laser A emits a light of wavelength lambda equals 600 nanometer and it travels in air with a speed c equal 3 times 10 to the power 8 meter per second. Is this light visible? Justify. In the visible spectrum, we have noticed that the range of visible wavelengths lies between 400 and 800 nanometer if the wave is propagating in vacuum. Then yes, this light is visible since its wavelength ranges between 400 and 800 nanometer. Calculate the frequency of this light. You are given the wavelength and the speed of propagation. Then applying the formula C is equal to lambda times F implies that F is equal to C divided by lambda. But here you need to take care that the wavelength should be in the SI unit since the speed is in meter per second. From nanometer into meter we multiply by 10 to the power minus 9. Substituting the numbers or the values in the equation gives us 5 times 10 to the power 14 Hertz. In the third part, you are asked to indicate the type of this light wave. It is a light wave, an electromagnetic wave, then it is a transverse wave. Another laser B emits a light of wavelength lambda prime is equal to 500 nanometer. Which laser emits the highest energy? We have said that the energy depends on the frequency. The higher the frequency, the higher the energy. As lambda decreases, the energy increases, so laser B, which emits the smaller wavelength lambda prime equal 500 nanometer, has the highest energy, since the higher the frequency, the shorter the wavelength. To summarize the ideas of this video, waves are either transverse, where the direction of vibration is perpendicular to the direction of propagation of the wave, or longitudinal, where the direction of vibration is parallel to the direction of the wave's propagation. The two natures of waves are mechanical and electromagnetic waves. In mechanical waves, they are produced by a source of mechanical vibration, whereas electromagnetic waves are produced by oscillating charges. Mechanical waves can propagate only in material mediums, and they cannot propagate in vacuum, whereas electromagnetic waves are capable of propagating in vacuum as well as in any other material medium. Mechanical waves could be either transverse like sea waves or longitudinal like sound waves, whereas electromagnetic waves are only transverse waves. This is the end of Chapter 7, Vibrations and Waves. Thanks for your attention.